All right, guys, good morning. We're going to go ahead and get started. I want to finish up. We have one more topic for the parallel topic sheet I want to cover, and then we're going to move on to series parallel circuits. So what I want to talk about, we talked about voltage sources. We talked about voltage sources in series. I showed you two ways to connect voltage sources in series. If I connect voltage sources in series so that I have opposite polarities facing each other, plus and minus. And what this does is it increases voltage. This is called series aiding. I also showed you a way to connect these in series where I have this polarities facing each other. So I might have it like this, where I have positive facing positive, or flip it the other way. Where I have a negative facing a negative. And this is called series opposing. Here, if I want to find the total voltage across the two voltage sources, I would do a subtraction. And here, I'm going to do an addition. Most of the time, you don't want this. I mean, there are certain applications where you come up or you run up against a series opposing connection of voltage sources. Most of the time, when you're connecting voltage sources in series, you do that to increase the voltage. So we connect voltage sources in series to increase voltage. So why would we connect voltage sources in parallel? So let's look at a situation where we might have, let's say we have two batteries and I want to connect them in parallel. Well, if I want to connect these two batteries in parallel, then they have to have the same voltage rating. So let's say this is 9 volts and this is 9 volts. I can take a wire and tie it from here to here, and take another wire and tie it from here to here, and now those two voltage sources are in parallel. Notice I have the positive terminals connected to the positive terminal and the negative terminal connected to the negative terminal. This is kind of like when you jump a car. You put the jumper cables on the good battery, you connect them to the battery you're going to jump, and basically you have a parallel connection. Well, if I put my voltmeter across this first battery, I read 9 volts. If I walk across here, across the second battery, I also read 9 volts. So hooking the batteries up in parallel doesn't increase the voltage. So what's the purpose of it? Why hook batteries in parallel? What do I get for doing this? Well, it turns out that batteries have another rating. We talked about ampere rating. We talked about cold cranking amps. We talked about several ratings for batteries. Another rating is the maximum current capacity. Every battery has a maximum current capacity, a maximum amount of current that they can supply to a load or to a device. And so let's say I have two batteries. Let's say the maximum current capacity of this battery was 10 amps. And the max current capacity of the second battery was 10 amps. If I connect between these 2 points over here, now my maximum current capacity is 20 amps. Doesn't mean I'm putting out 20 amps. It means that between these 2 points, those two voltage sources working together can supply up to 20 amps of current. If I had a situation like this, I have a battery. Say we have a 12-volt battery. It's 12 volts, but the max current capacity is 10 amps. And over here I have a motor, and that motor requires 12 volts, and that motor is going to pull 20 amps. If I hook this motor up to the battery, it'll probably run because it's getting 12 volts, but it won't run correctly because this battery can't source enough current. This battery cannot provide enough current to the motor, so it won't run at full speed or full capacity. So what I would do here is get a second battery, hopefully like the first one, 12 volts, 12 volts. And if the max current capacity of this battery is 10 amps, the max current capacity of this battery is 10 amps, now this motor is getting 12 volts, which it needs, but also the batteries can supply in this line here a total of 20 amps. And so the battery's happy. Now, typically, if you were going to do something like this, if that motor's pulling 20 amps, you probably don't want to top this out at 10 amps and 10 amps. You probably want to be a little bit more. So, you know, practically, maybe this is a 15 amp max current capacity, and this is a 15 amp max current capacity. Now, the two voltage sources working together have the ability to put out 30 amps. So you probably want that to be a little higher than what the load is going to pull. Question.
Sorry, Professor. Sorry. On that way, we are not to increase the volts, but we are increasing the capacity. That is the power.
Not the power. Not the power. The current capacity. The current capacity is the ability of the battery to provide current. Okay, so not increasing. You're increasing the power of the system because the current is going up. But the idea here is that if this first battery can put out a maximum of 10 amps, and if this second battery can put out a maximum of 10 amps, suppose I took these two batteries and put them in a box so you couldn't see them. So I put them in a box like this, and I hid that from you. Then over here, this thing in the box will put out a maximum current of 20 amps. So as long as I'm at 20 amps or below, I'm good. If I try to pull more than 20 amps, it won't work. It won't provide that. So by putting batteries in parallel, you increase the current capacity of the sources. The max current capacity goes up, not the voltage. So that's important. Did I answer your question?
Yes.
Anybody else have any questions? I have a question. Here's my question. So what happens if we do this? Remember when I said that when you connect batteries in parallel, the voltages must be the same on the battery. I mean, by definition, a parallel circuit has the same voltage across every element. So what happens if I don't do that, though? What I said before was, if I want to connect batteries in parallel, let's say I got a 12 volt and a 12 volt. I can connect these in parallel because the voltages are the same. So anytime you connect batteries in parallel, the terminal voltage of the batteries must be the same. So my question is, well, what happens if they're not the same? What if I ignore that and say, all right, I don't care what they say, I'm going to connect this up to a 9-volt battery. I'm going to take my 12-volt battery and connect it to a 12-volt battery. What do you think will happen in this case? Anybody? What do you think will happen?
Would the 9-volt battery start to get overloaded?
Close. Close.
Will 12-volt battery might get overworked then, or it might be imbalanced?
Okay, yeah, you guys you guys are focusing on the 9-volt battery, which is good. You know something's wrong with that. Let me show you something about batteries. I want you to write this down. I don't know if this is in any book. I mean, it's probably in the book somewhere, but it's not in your book. So anytime you have a battery or any kind of source of power, it could be a battery, a power supply like we have here in the lab, or any kind of thing that provides power. I'll show a battery, but this works for anything that provides power. So typically when I draw the battery, here's the positive terminal and here's a negative terminal. Well, think about current. If current is flowing in this circuit, current is flowing like this. So here's what I want to show you. Anytime you have current flowing out of the positive lead of something that's producing power, wall outlet, a battery, power supply, no matter what it is. Anytime you show current leaving the positive lead of some device that's providing power, then this thing is actually giving up energy. It's giving up energy and giving it to something else. If this is a resistor over here, it's giving that energy to a resistor. If it's a cell phone, this is giving energy to the cell phone. It's giving up power in some kind of way. It's delivering power. If I show it this way, though, suppose I have a battery. And I see current going in this way. I have current. Current is supposed to come out of the positive lead. Here I'm showing current going into the positive lead. Well, here when current is coming out of the positive lead of a power source, that power source is providing power, delivering power. If I show current coming into the positive terminal of the power source, it's absorbing power. And when something absorbs power, it's going to heat up. So resistors absorb electrical power, electrical energy, and then that radiates that heat off. It warms up. So where would this work? Where would you see a situation like this? Well, your car is a perfect example of this. What's the purpose of a battery in your car? What's the purpose of the battery in your car? It has one purpose and one purpose only, or maybe two purposes. What's the main purpose of the battery?
Start the engine.
To start the engine. Now, I know some of you might be surprised, but that's it. The only reason why you have a battery in your car is to start the engine. Well, if you're one of those guys or girls that like to sit in the car with the engine not running and listen to the radio, all right, you can use a battery for that too. But the main purpose of a battery in a vehicle, anything with a combustion, is to start it up. Once it's started, if you wanted to, and I don't recommend doing this, but if you wanted to, once the engine is started, you can carefully remove the battery and set it on the ground. The car will keep running because at that point, the battery's running off of what?
That's when it's running off the engine power off of that.
It's running off the engine power, the alternator or the generator. And somebody said, oh, you just said hi. So your car has an alternator or generator in it. The engine now is turning the generator, providing electrical power. So you don't need the battery anymore. The reason you need the battery is when you're sitting there and the car's not running, the alternator is not working because the engine's not turning. So you got to have something to power the engine to turn the alternator so the alternator takes over from the battery. But here's how the alternator is connected up in your car. What you have inside your car is a 12-volt battery. So you have something like this. Now say you're looking down at the battery. You're above the battery looking down at it. So here's your battery. You got a terminal here and a terminal here. And this is 12 volts. Well, connected to your battery is a generator or alternator. And it has a belt around it, and when you turn the engine on, that engine turns that alternator and produces electricity. If you take me for AC, we'll talk about exactly how that works. And I'll actually show you a demonstration in class of how that works. But the alternator has a red wire coming from it that connects to the battery, and it has a black wire coming from it that also connects to the battery. And the reason it has that is because when you're driving the car, the alternator recharges the battery. And so I want to show you something. Let me remove these wires from the alternator. And let's say you're listening to the radio over here. Here's your radio. And you're listening to it. Well, if you listen to the radio, then that radio has a connection to the positive terminal and to the negative terminal of your battery. So let's follow the direction of current coming from that battery to the radio. It's like this. Current is leaving the positive terminal going into the radio. And what I said earlier was, is if I have a voltage source and current leaves the positive terminal, then that battery is providing power to something. So current is leaving the positive terminal of the battery. It's providing power to the radio. Well, if you start the car, you also have a. I'm going to disconnect this because I don't want you to get confused. But the alternator is connected like this. It has a red wire coming from the alternator, which comes from the positive polarity of the alternator, and it has a black wire coming from the alternator, which is the negative polarity of the alternator. And so when you start the car, the alternator turns, and now current flows. It can still flow into the battery, to the radio, but current flows into the battery like that. It would be like current flowing this way into my car battery. So now this thing is absorbing power. And when something absorbs power, what it does is it heats up. Because, well, I should say absorbing electrical energy. It's going to heat up because it's going to dissipate power. So car batteries are rechargeable. What you'll do here is that alternator will recharge that battery. But at that point, the battery's acting like any other kind of load, like a resistor or a light bulb. Anything that you hook up that's absorbing power is going to heat up. That battery's going to heat up, get a little warm. It's going to absorb power. So the original
would not offer the power.
Say that again?
Well, does that mean that in this scenario, the 12 volt and the 9 volt battery, would the 9 volt not only absorb power, but it would also not be able to add its current to the system?
It's not adding current, it's taking energy away from the system. It's not adding anything to the system.
Okay, so it turns into a transducer rather than a voltage source at that point.
You're right. Basically, it turns into a transducer. But look, if you have a rechargeable battery, here's the thing. Say that I have two instead of a 9 volt. Say I have a 12 volt and a 12 volt battery. Some batteries are rechargeable. Some batteries are not rechargeable. So a car battery I can recharge. You guys are familiar with the cells that you may be using the toys. Some of those are non-rechargeable. So let's say these are rechargeable batteries, and this thing discharges down to 9 volts. Okay, so then I hook this one up to it. I take a wire and hook here. I take a wire and hook here. This battery now, current is going to flow out of the positive terminal of the battery and into the positive terminal over here. So that means this one is delivering power and this one's absorbing that power. And if this is rechargeable, what's going to happen is this first battery is going to discharge and the second battery is going to try to charge up. It's going to take energy from the first one, and they're going to meet voltage-wise in between. The equilibrium will be, this is going to, whatever's in between, what's in between, is 11, 10 and a half or something. This is going to discharge, and this is, ideally, it's going to meet at a voltage exactly in between the two. Now, not all batteries are rechargeable, and let's say this is not rechargeable, then this thing is just going to heat up, and it's going to absorb power just like a resistor. It's going to absorb electrical energy and heat up and radiate power just like a resistor. So this is not something you want to do. Typically, you want your voltage sources to, if you're going to hook them in parallel, the reason you're doing that is not to use one battery to charge another one. The reason you're doing that is because you want to increase current capacity. But what I wanted to bring to your attention is the fact that if you do have a power source and you see a power source with current leaving the power source out of the positive terminal and it's providing power, if you have a scenario where you have current entering the positive terminal of a power source, it's absorbing power. So providing power, absorbing power. Not really part of the discussion, but I thought it was interesting. Anybody have any questions over that? Excuse me. So batteries are kind of cool. I know some of you are electromechanical students, and you know, one of the big things is you know, more of these car manufacturers are excuse me, starting to add to their fleet electric vehicles, EVs, and there are schools, colleges that their engineering departments, students will build electric vehicles and they'll race them, they'll compete. And it's they have a lot of, I mean, you guys know they have electric scooters. They have a lot of things now that run off of electric motors, because now they can make the motors much smaller and much more powerful. And battery technology is getting better, where they can make batteries lighter, smaller, and more powerful. So there's situations where you can hook up batteries. You know that if I have batteries that, if I need more voltage, say I'm designing an electric vehicle, I'm making an electric race car, go-kart or something, and I need more voltage. So you know if I need more voltage, I can take batteries. Maybe I need, I got a battery here, a battery here. Maybe this is 10 volts, and this is 10 volts. Well, if my motor is going to require 20 volts, then I can hook these in series, and that'll increase the voltage. But what if I need more voltage and more current capacity? Because maybe the current capacity of this is 10 amps. Let me use another number since I use 10 volts. Maybe the current capacity here is 20 amps, and the max current capacity here is 20 amps. If I put them in series, I don't get 40 amps of current capacity. I still got 20. The only way to get more current capacity is I got to take more batteries and put those in parallel. So maybe I got another 10 volt and another 10 volt, and the current capacity of each of these is 20 amps. So now my max current capacity, you might think it's 20 plus 20 plus 20 plus 20, but it's not. This current capacity right here, that series connection of voltage sources, is 20 amps. And the current capacity right here of those two series voltage sources is 20 amps. I put them in a series, I don't increase the current capacity. It's only the parallel combination of those. And so the actual current capacity out here, I've doubled it now. From one battery, I get 40 amps. So if I have an electric motor that requires 20 volts, and I need maybe 35 amps to drive it, I can hook up a situation like this. So the point is that once you start combining these in parallel and in series and even series parallel, this can get kind of complicated. Okay, but we're not really there yet. Here's the takeaway from this, though. I want to move on to this circuit over here. The takeaway is I want you to know why you hook batteries up in series and why you hook batteries up in parallel. We hook batteries in series when we want to increase voltage. We hook batteries in parallel when I want to increase not current, but current capacity. And if I need some combination of the two, I can hook up something like this to increase both voltage and current capacity. Any questions over the discussion on batteries in parallel? Questions or comments? All right, well, let me give you a new term. Write this down somewhere. I'm going to hook up resistors in parallel, two resistors in parallel, two different ways. So here's the first way. So this is R1, R2. One way to hook these up in parallel is to take a wire and tie the top ends together, take another wire and tie the bottom ends together like this. Now these two are hooked up in parallel. Maybe though I want to hook it up like this. Maybe I don't have any wire to connect them. So what I do is I get the two resistors, the ends of the two resistors, I just twist them like this. I take one resistor, I take the other resistor, just twist it to it like that. And I connect the wire here and the wire there. So again, I got the top ends tied together and the bottom ends tied together. So these two resistors are in parallel. As a matter of fact, these two circuits are exactly the same, other than the way they look, exactly the same. The resistors don't care how you connect them. The resistors don't care if you connect them together with a piece of wire, or if you just take the leads of the resistor and you twist them together. It doesn't care about that. So these two circuits are exactly the same. They're equivalent circuits. But here's what I want you to look at. You see that I'm going to draw like a little circle around the top end of this. See this? I'm going to draw this. How many wires cut through that circle that I drew? How many wires cut through the circle?
3.
3. Got one right here, one right here, one right here. 3 wires. If I do the same thing down here, I got the same situation, don't I? I got 3 wires cutting that circle. One right here, one right here, one right here. So I want to define a new term. The new term is node. N-O-D-E. N-O-D-E. A node is a connection of 3 or more wires. If you draw a circle around the node, it's going to cut the circle in at least 3 places. Okay, so hopefully from the picture you can see that. And if these 2 resistors and these 2 resistors are the same, both of these circuits are exactly the same. Doesn't care how you connect the tops and bottoms together. So let me draw this another way. If I have this circuit and I connect it to a voltage source, but this time I'm going to add a resistor right here. See, before I added that resistor right there, this was kind of all one connection point. But when I add the resistor, when I break that wire right there, I break this side of the wire and this side of the wire. So now these are different connection points. If I draw a circle or a box around this top one, I see that that box is cut at 3 points. It's cut right here, and right there. So this is a node. And I have the same thing on the bottom, right? I can do this like this. I see that it's cut at 1, 2, 3 places. So this is a node. So one thing I want you to see here is that nodes can, nodes can only happen when I have things in parallel. You see it? There's no way to get a node out of this if these were in series, because I need 3 points cut in the circle or square, not 2. So if I have a node, then by definition, something's in parallel. Now, usually what we do is we name the node A, B, C, D, and so forth. So I'm going to call this node A. I'm going to call this node B. Now, what do I know about the voltage across R1 and R2? What do I know about the voltage? Anybody?
It's the same.
It's the same. How do we know that? Well, because we learned that in a parallel circuit, the voltage across the things in parallel is the same. Now, I added this resistor to it, so it's really not a parallel circuit. It's really a series parallel circuit, but we'll get to that in a minute. What I do know that is if I hide this part of the circuit, then that looks like a parallel circuit to me. And in fact, they are in parallel. So what I know is the voltage across resistor 1, we can call that V1. The voltage across resistor 2, I can call that V2. And what I know is that they got to be equal because they're both in parallel. And since they're both in parallel and the voltages are the same, we really don't have to subscript them. We can just call them V if we want to. But what I wanted to show you is sometimes what we do is we name the voltage not in terms of the resistor or resistances. We can name the voltage if things are in parallel in terms of the node. So I can call the voltage across this one V1. I can call the voltage across this one V2. Or I can call the voltage across both of those VAB. The voltage from node A to node B. Now, this is called, when you write it that way, it's called double subscript notation. Double subscript notation. You can write that down if you want, but don't worry about how it works right now because there's a lab on it, and when we get to the lab, we'll study this in detail. But for now, I want you to know that I can call this V1, I can call the voltage across this one V2. I can call this voltage across both of those VAB, the voltage from node A to node B. And when you see that, you know something's hooked up in parallel just from the diagram. That's the first thing I want you to be clear on. The second thing I want you to be clear on is this. When I draw the nodes spread out like this, I draw it spread out like this, so that's a node. Or I can draw it like this, connect it together, like that. So we got a node here and a node here. And if these resistors are the same as these, then these two circuits are exactly equivalent. But what we say is that these nodes right here are expanded, and these nodes, when it becomes a dot, are collapsed. The resistors don't care. The voltage source doesn't care. Both circuits, if I hook a battery up to this one and this one, both circuits look exactly the same as long as those resistor values are the same. So it doesn't care how it's hooked up. So the term node, you should be clear on what we mean by that. Understand that the fact that we can name a voltage between the nodes, this is a node voltage, and the fact that a node could either be a piece of wire or just a little connection point like that, we think of this as a node being expanded, and this node here is collapsed, and these two circuits are equal to each other. That's a sideways equal sign. Does it make sense? Let me show you how we use this. So I have a circuit over here, and this is not a series circuit. It's not a parallel circuit. It's actually a series parallel circuit. Part of it is parallel, part of it is series. So let's say that I took these two resistors and I put them in a circle. Now we're looking inside the circle, and you can see that there's two resistors in there, a 6 ohm and a 3 ohm. But just act like we couldn't see in there. Act like we can only see the circle and it's covered up. We couldn't see what was behind the circle. Then if you redraw this circuit, what you would have is the voltage source, which is 36 volts. You have R1, which is 2 ohms. And then you have this circle. I don't know what's behind the circle, but I just know it's a circle over here, like that. See, if I hid these two resistors in the circle, then you can see that R1 is in series with this circle thing. I don't know what's in there, but it's in series with it, whatever it is. So this is the series part of it. Current that leaves the voltage source comes through R1, and that same current goes over to this circle. And remember, in a series circuit, everything gets the same current. Now, if I look inside of here, now I see that inside of here, I actually have a resistor in parallel with another resistor. So that's the parallel part. So here's the series part, and here's the parallel part. So we call this a series parallel circuit, or a combination circuit, combination of a series and parallel together. And so the question is, now how do we solve a circuit like this? And this is what I want to talk about this morning. How do we solve a series parallel circuit? So there's a method to it. Now you will need your coloring pens and pencils. So if you didn't have a chance to get those, please get those right now, and you need some paper. Coloring pens or pencils and paper. And you will need those coloring pens and the straight edge for the rest of the semester. If you take me for AC, I'm pretty sure I'll be teaching that, then you'll need it for AC too, so just keep it with you. So how do I solve a circuit like this? Now, when the method I'm giving you only works for circuits where you know all the values. So what I mean is, let's say I knew this was 36, this was 2, this was 6, but I don't know what this resistor is. I just leave it like that. They want me to solve the circuit. Then you know the way I'm going to show you, that's not the way the approach to solving. This is called unknown values, random unknowns. It only works, the method we're going to look at now only works if I know all the values for the resistors and all the values for the voltage, or voltage sources. But assuming you got all that information, here's what you do. You start with the part of the circuit furthest away from the voltage source. So write this down. To solve the circuit, start with the part of the circuit furthest away from the voltage source or power source. So if the power source is over here, I'm going to start on this side. If the power source is over here, I'm going to start on this side. If the power source is right smack dab in the middle, I'm going to flip a coin. It really doesn't matter which side I start on. But for this circuit, the power source is on the left, so I'm going to start over here on the right. So I'm looking on the right, and I ask myself, what kind of connection do I have between components? They're either going to be in series or they're going to be in parallel. And so if I start over here on the right, just looking at these first two resistors, I see that these two are in parallel. That means I have a node. So what I want to do is anytime I have something in parallel, I want to identify and name the nodes. So that's the first thing you're going to do. I got a node right here. And I got a node right here. And I like to shade these nodes in. You don't have to, but I like to shade them in like this. So I start with the part of the circuit furthest away from the voltage source, and I look to see if I have something in parallel. If I do, I identify the nodes. I just shade them in like this. And notice I'm using the same color for those nodes. And then I'm going to name them. I call this one A. Call this one B. Once I've identified all the nodes, then what I want to do is start combining stuff. Now, here's what we're trying to do. Ultimately, what I want to end up with is a series circuit. So I'm going to combine things in series, or I'm going to combine things in parallel, and I'm going to keep doing that and keep redrawing the circuit until I end up with a series circuit. Well, fortunately for this, we only have to combine two resistors to end up with a series circuit. I'm going to combine R2 and R3. So I'm going to combine those into a new circuit, and that new circuit is called an equivalent circuit. So let me show you what that looks like. I'm going to draw this circuit exactly like you see it here. But I'm going to combine these two right here. So I have the combination of those two. I'm going to call that 6 parallel 3. Actually, I'm going to call that R2 parallel R3. Now, I don't know if I showed this sign before, but if you have R1 in parallel with another resistor, you can show it like that. If they're in series, you show it like this. So that means that the resistors were in series, and this means that they're in parallel. So when I name this resistor right here, I'm naming that R2 parallel R3. And then what I want to do is say, all right, well, what is the value of, if these two are in parallel, what's the total resistance of R2 and R3? What's the equivalent resistance? If I take 6 in parallel with 3, how many ohms is that? Can somebody figure that out for me? How many ohms is this? It is 2 ohms. Well, how'd they get it? Well, there's a couple ways. You can use 1 over R EQ equals 1 over 6 plus 1 over 3, like we learned a couple days ago. I can use that 1 over R rule. Probably the easiest way, though, is to use the product over the sum, because these are nice numbers. Product over the sum says that I can find the total resistance by taking the product of the two resistors, so 6 times 3, over the sum of the two resistors, so 6 plus 3. On the top, I get 18. On the bottom, I get 9. So this is 2 ohms. So you got to be able to apply those formulas from parallel. Now, here's where students start to have trouble in the course, because this is what I was trying to explain in lab the other day. Everything you learn in this course is dependent on what came before it, right? So if what came before it, if you're weak on those skills, then you're building a weak foundation. And we're just going to keep building right on that weak foundation. You know what's going to happen. If the foundation is weak, it topples over. If the foundation is strong, it'll support everything that comes after it. So if you're, if you're having trouble, working with this kind of stuff, you got to be really good at series. You got to completely understand parallel. So when we put the two together, it'll be way easier. So if you're having trouble with things, you want to make sure you get with me, because this is as easy as it gets. Everything from here just gets more and more and more complicated. You can do it, but you got to apply yourself. So something like this, you should be able to, right away, you should know how to get that, and be able to use that reciprocal key to come up with an answer quickly, else you won't have enough time to finish the exams I'm going to give you. Well, anyway, I started with the part of the circuit furthest away from the voltage source. I labeled and named the nodes, and then if I have nodes, that means I have something in parallel, so I combine those two, in this case, two resistors in parallel, and I end up with this equivalent circuit. Now what I got to do is move my node from here to here. You might say, well, hold on a second, Singleton. That circuit over here don't have any nodes. You said a node has to cut a circle in 3 places, and it does. So what I really want is, where did the node go? Where is the node in this diagram? Well, that point right here, actually, I don't know where it is, but it's somewhere inside of that circle. And the reason I know that is because I know it's between R1 and these two resistors, which we're calling R2 parallel R3. I know it's somewhere between that, so I'm just going to circle that wire right there and say, well, that node is kind of disappeared in there, and the bottom node is somewhere in that circle. It just kind of collapsed and disappeared. What I do know is that the side of R1 is connected to node A, the side of R1 is connected to what I'm calling node A inside this circle, and the tops of these two resistors, which are now represented by that single resistor, is connected to the other side of that circle. So I'm going to just kind of over here show where those nodes used to be. And now I've changed this circuit into this circuit, and here's the thing. This battery right here has no idea that there's 1, 2, 3 resistors. You can take the battery and move it from here to here. It doesn't know that you moved it. It still sees the same amount of opposition. Matter of fact, not only does it not see these 3 resistors, it doesn't even see the 2 resistors here. How much resistance does this voltage source think it's hooked to? Well, from this circuit, you can clearly see that the total resistance of this circuit is 2 and 2 is 4. So even in this circuit where you have 3 resistors, that battery thinks it's hooked to a one resistor that's 4 ohms. It sees the total resistance. That's all it can tell is total resistance, which is interesting. Once we get to the series circuit, though, what we're going to do is solve the series circuit. Now, here's the power of what we're going to do, the power of this method. I call it the method of redrawing. You redraw the circuit until you get down to a series circuit. You solve the series circuit, and then the information you get in the series circuit, you put that back in the original circuit, and that series circuit is going to help us solve the more complex circuit. Now, it's hard for me to say, it's way easier for me to do, so let me just show you. I'll show you this, and we won't have enough time to do one. I think we'll be out of time. But we'll pick up next week, and then I'll give you some more practice. Not next week, but Friday, and then you'll be able to do some practice. But just kind of watch how this works. Let's solve this circuit. So when I solve a series circuit, I got to find current. I got to find voltage drops. I could find power if I wanted to, but not in this case. So let's solve the circuit. Well, if I solve the circuit, I want to find the total resistance, which is easy. I got 2 and 2. I got 4 ohms. So RT is 4. And I can use that total resistance to find the total current. Well, Ohm's law says that current equals voltage over resistance. So I have 36 volts. I have 4 ohms. 36 divided by 4 is 9, and that will be 9 amps. So my current in this circuit is 9 amps. So I'm going to draw that like this. I'm using a certain color for all my currents. I'm using green. So I'm going to show the current going like this, and it's 9 amps. And just so it stands out, I'm going to put a box around here. And that box is not part of the circuit. It's like a meter reading 9 amps is what it represents. So I show the current as an arrow, 9 amps coming out of the battery. Then right away what I'm going to do is, I know I have 9 amps coming out of the battery, so I'm going to show it in this circuit coming out of the battery. I got 9 amps. I can see clearly that 9 amps is going to flow through R1, so notice I got 9 amps going to R1. So whatever you get over here, right away you transfer it over to the original circuit. Everybody with me so far? Nothing hard. We just found total resistance and use that total resistance to find the current. Current was 9 amps, so that means I have 9 amps coming out of the battery. I show it in this picture, and I show it in that picture. Well, what else can we get? I can also get the voltage drops. Now, in this case, normally to find voltage drops, the voltage across the resistor is equal to the current through it times the value of it, right? I know the current, I know the resistance, but I don't have to do that because I know that I got 2 resistors of equal value. This is 2 ohms and this is 2 ohms. So each one's going to get how many volts?
$18.
18. It's a voltage divider. This first resistor is going to get 18 volts. And I hope this red shows up. I don't know how it shows up in the camera. But across this first resistor, I get 18 volts. So I'm going to show it like this. And whatever I find over here, I'm going to show it the same way. 18 volts across that first resistor. And the second resistor gets 18 volts also. But let me show you something about the second resistor. Since that second resistor has nodes, then this 18 volts is a node voltage. It goes from node A to node B. That's important because when I show it over here, I got to show that 18 volts extending from node A to node B. And since I know that this is a node voltage, I know that the thing that 18 volts is across has to be something in parallel. And what I know is things in parallel have the same voltage. So that 18 volts here or here is across both R2 and R3 because they're in parallel. So I found the voltage. This circuit is solved now. I found all the voltage drops. I found the current. I really can't do anything else to this, so I'll move over to the next circuit, which happens to be original circuit. And I stand back and look at that and say, all right, what don't I know now? And I know everything. The only thing that's missing is the current in R2 and the current in R3. That's all that's missing. But if you look at it, I know enough to find that. To find current, I got to know voltage and I got to know resistance. That's the way I get current. Well, I know the voltage across both these resistors. I know the value of both those resistors. I can get the current through it. 18 volts on 6. 18 on 6 is 3. So that means I have 3 amps flowing this way. I'll just show it with a box around it. That's I2. And over here, R3, I got 18 volts across 3 ohms. That's 6. So I show 6 amps flowing like this, and now my circuit is solved. Completely solved. The only thing that I haven't solved here that I can ask you for was power. But look at this. If you solve circuits using this method, you know that power equals V times I, and you know V and I for each one of these. You got 18 volts, you got the current, you multiply 18 times 9, gives you the power here. You got the voltage across both these resistors, current through both those resistors. You multiply 18 times 3 or 18 times 6, it gives you the power dissipation for R2 and R3. The circuit is completely solved. So it turns out this method helps you to think about what's going on in the circuit in a logical way. Very, very, very powerful technique for solving series parallel circuits. And so the goal is we'll spend the next couple of days working stuff like this to get good at it. The idea is you want to get really, really good at solving series parallel circuits. So we'll spend time there. If you wonder what comes after that, then what happens is, all right, when you get good at solving really complex circuits like this, then I'll come in here and say, all right, well, what happens if you do this? What happens if I take this out and put a battery right here? Now, how would you solve that? If I got one here and one, that's a whole nother beast right there, but we'll get to that. So right now we'll stick to series parallel practice circuits. I'll post a topic sheet. I got one that I'm working off of, but I'll post, I think it's topic sheet 6. I'll post that at some point. You guys will have access to that. But for now, that's it for now, I guess, and we'll do more of this on Friday. Anybody have any questions or comments for me before we sign off?
So, Professor, if I better understand what you say, before starting doing a calculation for a second, for a second like this, I have to start on a parallel and finish a series. That is okay.
Mm-hmm. Yep. First thing is put these in parallel. Is that what you said?
Yes, yes.
Yeah. You put these in parallel. 6 parallel 3 gave me this 2. And then I want to end up with a series circuit. Are you asking me how we go from this circuit to that circuit? Is that what you're asking?
No, I was asking you when I got a second like this and you asking me to do calculation. So my first thing to start is starting by calculating the parallel resistance. After I finish that, I'm going back to do all on the, is that?
Yeah. You know, I can't, your microphone, I don't know what it is, but your microphone cuts in and out and it makes it almost impossible for me to understand what you're asking me. So you may have to ask me when you come here to school. I can't understand you. Your microphone's like muffled. Shelly, do you have a question? Do you understand what he's saying? Shelly, do you have a question?
Yeah, I think I understand what he was trying to say.
Okay.
So he's asking if, like when you have a series parallel circuit, do you start by calculating the resistance in the parallel circuit first, or do you go to do the series calculations?
Okay, so if I have, let's look at that. And that's a source of common error, so I'm glad you asked that question. Let me show you something real quick. Here's what some people do incorrectly. We'll use the same circuit. What was this? This was 6, 3, 2, right? All right, here's what some people do. So if I understand your question, you're saying, all right, do we come over here and we calculate these 2 in parallel, or do we do the series first? And what you do is you start with the part of the circuit furthest away from the voltage source. So over here, the thing furthest away from the voltage source is not these 2, but it's these 2. So I want to start with those. If I just look at those, ignore everything else, I see that these are in parallel. So I got to do those first. But what I wanted to point out to you is this, or to you all is this. How are R1 and R2 connected? How are they connected? Well, let me tell you how they're not connected. R1 and R2 are not in series. So if you're thinking, just from the way you guys asked that question, if you're thinking that, do I combine these first? Do I say that R1 and R2, do I add those up to get 8 because they're in series? These 2 resistors are not in series. Can you see why they're not in series? A series circuit would have the same current. If they were in series, then the current through R1 would only go through R2, and that's not what happens. You know that we got, I forgot how many amps was through here, but this current actually, some goes this way and some goes that way. So these two resistors are not in series. So you can't come in here and say, I'm gonna do the series part first, I'm gonna add this to that, because they're not in series. What's in series is, if I wrote this out, R1 is in series, that plus sign means series. R1 is in series with the parallel combination of R2 and R3. That's why I drew the circle earlier. This circle right here, this is in series with that circle. So if I drew it, now that's a series circuit. This resistor is in series with this circle, but there's something inside the circle. What's inside the circle is this. Two resistors that happen to be in parallel. So this is a series parallel circuit. R1 is in series with the parallel combination of R2 and R3. So I'm just saying that. So if you're thinking to yourself, well, I can add R1 and R2. No, you can't, because these are not in series. You can only add them when they're in series. And if this wasn't here, then these two would be in series. But once you connect this wire to here, and this wire, then this and this are no longer in series. If I draw this another way, you'll see it. Let's say I do this. Let's say I disconnect the battery from this. And I take these two wires and I bend it out like this. If I bend it out, here's what this would look like. You see this? Then you see these two. I guess this was R3. Oops. So if I redrew this, here's what you have. So this way you can see that you actually have R1 in series with the parallel combination of these two. So you can't just add this and that, or this and that, because they're not in series. So you got to understand the difference between a series circuit and a parallel circuit. So I hope that's what you guys were asking. I don't know if I covered that or not, but I know that's one common area of confusion. Students will see a circuit like this, and they'll get confused, and they'll say R1 and R2 are in series. I don't know why they're confused, because it's clearly a series circuit has one path. Clearly, there's not one path. There's two paths. There's one here, and there's one there. So there's no way that these two can be in series. These two are in parallel, and the parallel combination of those is in series with R1, but R1 and R2 is not in series. If that's the case, you might as well say R1 and R3 are in series, because you got the same kind of connection to it. So I don't know if I answered the question or not, but hopefully you can see the difference between when I draw it that way, that you got to come over here and work on this part of it first and turn that into one resistor. So I'm going to turn that into this. And we'll combine these and get this. And this is R2 parallel R3. I'll get 2. And that's what I did when I actually solved the problem. I got to combine the two parallel parts. But you got to first recognize that this and this are not in series. Or this and this are not in series. I got two resistors in parallel, and the parallel combination of those two are in series with R1. So again, I don't know if I answered your question, but maybe if I didn't, you can ask me again on Friday, or when we come together on Tuesday. You can show me on the board if it's not clear what you're asking me. Anybody else have any more questions?
I just wanted to make sure I got all of the main steps that you were talking about today. So step one, you had start with the resistor furthest from the voltage source, and you identify the nodes. From there, you draw the equivalent circuit into a equivalent series circuit. So that way, and you do that by doing the REQ to combine the parallel, so that way you can get the series. From there, you solve the series circuit to be able to find your total resistance. With total resistance, you can then solve for the current within that series circuit, using the current then to find the voltage drops.
Yep.
And then you finally solve the current for the parallel circuits.
That's it. Perfect. Exactly right.
Okay. I just wanted to make sure, because I was when I was writing down, like you were talking about a few other things, and I just really wanted to make sure I didn't miss any of those steps.
So you got all the steps. Now, for this circuit, we did it in 2 steps. We went from the original circuit to the series circuit in 1 step. Now, they won't all be that way. You might have to draw 2, 3, 4, 5 circuits to get to that. But what you do is just keep redrawing and combining, redrawing and combining. Eventually, you'll end up with a series circuit, and then you'll transfer all the information back to all the previous circuits. And you'll move over one, and the circuit will help you understand the next. It's kind of hard to explain, but each circuit, when you work your way back to the original one, each circuit helps you solve the next circuit. So here we did it in 1 step. Next time we get together, I'll show you maybe one where we need to do it in 2 or 3 steps. When we get more complex circuits, it takes more drawing to do, but yeah, you got the steps down right, and it was perfectly said.
It's almost like the like different sections are almost like different parentheses within the equations of first you do this set of parentheses, and you do these set of parentheses, and the more circuits you have, or the more parallels and the more series, basically the more parentheses you're adding on to this equation.
And matter of fact, since you say that, Dr. Whaley, I don't know if you guys know Dr. Whaley, but he's the chair of the department. What he does is he doesn't even he just gives you this. He'll say, all right, how do you find RT? And you got to say, all right, well, the first thing I got to do is put these in parallel. So over here, then you'll say, you write this R2 parallel R3. And then I got to take this equivalent resistance, which means you got to put parentheses around it, because I can replace these 2 with one resistor, then I can put a plus sign because the thing that's going to do it next is that. So he'll just, and you'll have parentheses inside parentheses. So that's exactly the way you think about it. Matter of fact, this is actually a good exercise to do that. I mean, he does this, but I don't know. But yeah, the way you're thinking about it is perfectly correct.
Awesome.
Perfectly correct.
Thank you so much, Professor. Have a great rest of your day.
You too. Thank you. Anybody else have questions?
No, it's good. You have been clear now.
Okay. Well, we'll do more of this. I think as we do more, this is just one problem we looked at. It'll get real clear. This is not particularly difficult. You just got to get used to it, and it's actually kind of enjoyable once you see what you're doing. So we'll do more of this, and guys, we'll work on this until everybody gets it. Anybody else before I sign off? Guys, have a great rest of the day. I will talk
Professor,
to you.
I have one more question.
Mhm.
I wasn't there for Tuesday. Is there any way I can make up the lab, or do I have to come in next class?
Well, typically, if you can come in, I have time between on Monday and Wednesdays between 10 and 1, or on Tuesdays between 12 and 6. Now today won't work because I'm actually going to leave campus here and come back at 1. But let's say that you wanted to come in Monday. You know, come in Monday. Since you have lab, what time do you have lab on Tuesday?
10 a.m.
If you wanted to, you could come in and do the lab. Actually, we didn't have a lab last week.
Oh, so we didn't? Oh, okay.
You know why? Because I was going to have the lab, but the exam scores were so low, I decided to cancel the lab, and then we went over the exam. That's what we did. So you didn't really miss anything. You missed the explanation of the exam, but I can send you a link to that if you want to watch that. But we went over the exam, so we didn't have a lab.
Okay, sounds good, Professor. Thank you.
See you later.